All right, everyone. Thank you so much for joining us. I guess let's start moving forward with the next speaker. Again, if you have any audio issues or anything like that, please let us know. Scream at us. The next talk is going to be by Simon Horman about hardware offloading. Please, Simon, please take it away.
Thank you. So my name's Simon. I'm the chief scientist of SmartNICs at Corigine. Corigine is furthering the work that Metronome did on the network flow processor. And today I'm going to talk about the hardware offload of QoS. All right, so there's going to be 3 sections today. I'm going to give a little bit of a background on rate limiting. I'm going to give an overview of the design for metering and how, for hardware offload of metering, which ties into the TC Policer action. I'm then going to cover 3 open issues, one of which actually was closed between when I wrote the slides and today. So let's get going. Okay, rate limit. So rate limiting is one of the oldest features, oldest QoS features of OVS. I can distinctly remember doing a project on this area a very long time ago, maybe 15 years ago. How does it work? It's pretty simple. You set up a rate limit that can be applied to a port, and off you go. Recently, we made some changes to this, or some enhancements to this. Previously, it could support byte rate, bit or bit-based rate limiting, so you however many megabits per second, this kind of thing. We also added a feature, so you can also do packet-based rate limiting. And the reason for this is in the Chinese market, in the Chinese cloud server provider market, typically when you buy an instance, it has various attributes such as the number of CPU cores and the amount of memory, but you also get attributes of the networking, and this is expressed as bits per second and packets per second. This is the way things work, so we wanted to support that feature. It's pretty straightforward. It's cut off slightly in the slides here, but as well as being able to specify the rate in terms of bytes per second, you can also specify kilopackets per second, and you can do both at the same time. So the basic part, the basic way that rate limiting works, which I forgot to cover, is that you have a limit, and when the limit, the rate is less than the limit, the packets pass through, and when it's over the limit, they're usually dropped. So the TC Policer is part of the TC subsystem of the Linux kernel and has been for an extraordinarily long time. And it provides very similar functionality. So you can express rates in terms of packets per second, in terms of bytes per second, and it was recently enhanced to support the feature of doing packets per second. And it is actually the TC Policer, which since the beginning has been used as the backend for the kernel datapath implementation of rate limiting. So it was very natural to extend it in this way to support this new packet per second feature. And it also provides an offload feature. The kernel offload of OVS is all driven by TC filters, which are flows and actions. So this is an action. We can offload it. Everything is nice. Okay, so a more sophisticated feature of QoS feature, which was added to OVS significantly later than the one I just discussed, the rate limiting, is meters. And this is kind of the meat of the talk, where I'd like to discuss the similarities between meters and police actions and how we were able to model the metering using the police action and in software, and then in turn that led to an easy way to offload it because TC is already used for hardware offload. Okay, so here's a kind of overview of how open flow meters work, or some key attributes of them. So they have a number of bands. each band has a target rate or a target rate, but the rate might be in bytes or packets. You can do two things. If the rate is exceeded, you can either drop the packets or you can mark the packets. Now, for the purpose of this work, I'm only handling the drop case because that is what our users request. But there's no real reason you couldn't extend it to handle the SCP case. Meters are independent of flows. So what does that mean? It means that more than one flow may use the same meter. I'll show an example in a minute. And they're also independent of ports. So regardless of, well, we know that flows are linked to ports, but you can have different flows attached to different ports which share the same meter. So here's an example of configuring a meter using the OVS tooling. So firstly, we create the meter itself, and this has a couple of attributes. It has an identifier, which is number 99. That's just so you can identify it. And then it has a rate attached to it. And then in the for loop, what I've done is I've attached this meter or used this meter in 4 different flows. So for each of 2 ports, I've made 2 flows. And so what we have here is a limit of 1 megabit per second, which is applied to any packet which is IP or IPv6, which comes in to port 1 or port 2. It also outputs those packets to port 3 if the rate is not exceeded. So on the left of this slide is the same as 2 slides ago. This is the attributes of the open flow meters. And on the right, I compare this to the TC police action, which, as I mentioned, has been around for an extraordinarily long time. So there are some differences, but there's a very strong overlap. So the police action is only single band. This is perhaps the biggest difference. However, you can chain police actions, which allows you to effectively create a multi-band composite. I'll also add that for the use case I'm interested in, we only use a single band anyway. It has a rate that passes in. It may drop packets. It doesn't natively allow you to mark packets, but you can combine the policer with another action which will do the marking. So this is also possible. Now, what a lot of people don't realize about TC actions is you can create them independently of the flows or the rules or the filters. They're all different words for the same thing. Usually, maybe the most common way to instantiate a filter is you instantiate the filter, and in line, you also instantiate the actions. So these actions belong to the filter. However, it is also possible to approach things a different way, which is to create an action. And then when you create a filter, to use that action by reference. And in this way, you can use the same action instance in more than one filter. And so usually filters are attached to ports. However, because of this property that you can reuse the same action in different filters, you can create different filters which are attached to different ports, which make use of the same action. So I did actually make this slide some time ago, and I very optimistically claimed that it was a very good match. I stand by that comment, but there have been some bugs found recently. We'll get to them a bit later. But in general, these things fit very nicely together, in my opinion. Okay, so this is similar to the previous example. The differences are that these are TC actions rather than OVS rules. And secondly, I left out the output to port number 3 because it just made it more. It added too much noise to the slide without adding any real value. But again, so firstly we create the action, index 99, and we give it a rate, in this case 1 megabit per second. And then we use that action in 4 flows. So for each of 2 ports, port 1 to port 2, we use this action if there's a match on IP protocol or IPv6 protocol. So this is the same without overlooking the fact that it doesn't output the packet. This is the same as the previous example. Okay, so I do hardware offload. Everything I do somehow connects into hardware offload. So what I was looking for was a way to do hardware offload of metering. There's already a software implementation. How can we do this nice? Well, the design that I came up with is essentially to extend the hardware offload portion of TC, which is called the flow rule API. And what I did was my design is to create a new top-level object. So a top-level object might be, say, a U32 classifier instance, or in the case of OVS, you would use a flower classifier instance. There are others too. What I wanted to do was to be able to use the same mechanism, but instead of it being an instance of a classifier, to be an action. And so we create TC setup action to achieve that goal. And the next major bullet point sort of glosses over a significant amount of work that had to be done, but essentially what we did was to modify the existing TC APIs, which handle things like creation and modification, deletion, and statistics. It handles them for the software, but it also handles them for the hardware. So we essentially had to teach the parts of it which could already handle creating and destroying actions. We had to teach it how to do hardware offload, which was a challenge. So I did present on this topic, I think, at this conference last year. And at that time, things had not been merged, but now they have. So this is very nice. The basic functionality was merged into the kernel, if I remember correctly, around about last December. And that included the modifications to the TC APIs, to flow rule, which is, so I make the distinction here because actually flow rule allows offload of both TC and then filter. And the NFP driver, that is the Corigine driver, followed pretty soon afterwards. Obviously, we developed these things together to test it. OVS itself came somewhat later, and it was actually a patch set from NVIDIA that got accepted. So thanks to NVIDIA for doing that. We also had a version, but the NVIDIA one was chosen. So that's where we are, and this is similar as of this slide to where we were a year ago, minus some delta. But recently, some issues have come up, so I'd like to cover them. Okay, so there are three. It says open. One of them has been closed. We'll go through them one by one. Okay, so this one is the one that has been merged, and this one is maybe the simplest of the three. So when you create an object, let's say a filter, you can set attributes of it, offload attributes. So you can tell it to skip hardware or skip software, or neither. So the default case is neither, in which case it will add it to software, try to add it to hardware. If that fails, that's fine. It just stops. If it succeeds, that's also fine. Skip software means it will only try to add it to the hardware. And if that fails, you will get an error. And skip hardware means it only added to the software data path, and it doesn't do anything with regards to hardware. Okay, that's fine. So we created this new type of object, which is the offloadable action instance. And during the development of that, it was decided it would be altogether much simpler to reason with if we required these flags to be the same for the action and any flow that uses it. Otherwise, sort of some weird corner cases can happen, and it wasn't really relevant to the use case, so we just decided to make this very simple policy. However, unfortunately, when the OVS code was added, there was a small oversight and where you can get a mismatch. So if you use the default policy, which is neither skip software nor skip hardware, everything is fine. There's no problem. But if you use one of these skip flags, it was only set for the flow, not for the action. So therefore, any action that you might be using, only police actions, which were created independent of the flow, there will be a mismatch. This mismatch would result in the flow not being offloaded. Therefore, if you had an offload policy of other than the default one, you couldn't do hardware offload of metering. That's a bit of a problem. The fix is quite simple. What we do is to basically, when we create these action instances, we use the prevailing policy, these flags, the skip hardware, skip software. Everything matches, everything is good. Problem is solved. Okay, next one. This is a nettlesome problem, but I think we're moving towards a solution. The problem here is when I thought that OpenFlow meters match releases, I made a mistake. I overlooked one important point, is that in OpenFlow there's a distinction between the meter action and the meter itself. Each flow has a meter action, and these meter actions, it's like a meter action instance, which is per flow. And then they call into a meter object, if you like, which might be common. In the TC model of things, these two things are conflated. There's a TC action instance, and that's it. So we can share the action instance itself, but there's no entity at that point in the flow which is unique to the flow. From a packet processing point of view, this presents no problem at all. But from a statistics point of view, it presents a problem because the statistics are incorrect. So there has been an update to this chart since I wrote this slide, but it's not fixed yet. So 3.0 was the first release that included metering, and it would count the statistics based on the police action. But the police action is shared between different flows, so you would end up with statistics relating to packets that went through a flow which is different, and this is obviously incorrect, and essentially is a form of overcounting. In 3.0.1, we added a patch to try to fix this, but unfortunately our understanding of the problem was not sufficient, so it's not actually a fix at all. What it does is to count things based on the action that immediately follows the police action. Now, in hindsight, it's obvious that this is not correct because any packets that are dropped won't get that far. So this becomes a form of undercounting. It's debatable which is worse. They're both incorrect. My colleague didn't want his incorrect patch in the tree anymore, so I reverted it. So in the next release of OVS, which will be 3.0.2, we'll go back to the previous behavior. But what is the fix? I mean, how do we resolve this? There seem to be two main proposals. I think that both of these will work. So the one that was discussed on the mailing list, which I think is the one that will prevail, is to add a dummy action, like a GACT action, which does absolutely nothing except collect statistics. And if we use at the end of a GACT action, you can set the control, and if you set it to pass, it will just keep going. So it really is a no-op from a packet processing point of view. This will give us the data we need. It turns out, at least in the case where there's only one meter, that you don't actually really need to do anything on the hardware offload side here, because essentially the way that the TC subsystem in the kernel collects statistics is you actually just basically end up with the statistics for the flow itself, without the hardware needing to record the statistics for these new actions, which is a problem because it's sometimes hard to change hardware, right? So I think this will work quite nicely, and I was hoping to post a patch before I stood here and talked to you today. And certainly there is a patch internally, but I wasn't comfortable with posting it. It's not quite right. But I will be able to post something for discussion there very soon. An alternate idea, which my colleague came up with, was just to simply count the flow statistics. I did discuss this at the NetDev conference a few weeks ago. The feeling in that discussion was that this was, although it will be correct, it was not desirable because essentially we'd have to have some new infrastructure and some new mechanism in the kernel just to handle this case. Whereas in the first case, although I feel it's a bit hacky, this first idea, it does allow you to reuse the existing infrastructure. So hopefully what will happen is in the next couple of days to weeks, I will post a patch, and then we will move forward with resolving this problem. Okay, last problem, nearly the last slide. Action eviction. So we have lifecycle problem. So usually what happens is you detected the flow is inactive, you evict it from the data path, everything is fine. This is the revalidator, it's very complicated, but it works. But we have these actions which have a different life cycle to the flows that they belong to. So an action might be used by 0 flows, well, then it shouldn't be instantiated in hardware, but it might be used by 1 or more. And only until the usage count gets down to 0 should you delete it. My feeling that the good solution to this problem would be indeed to reference counter and remove it at that point, but apparently that's easier said than done. So we're looking at various options. The one that we posted was to add a revalidator, but various people objected to the fact that this was quite computationally expensive. So now we're looking at the fact that we can actually detect that the deletion of the action failed, and then we can add it to a list of things, maybe to be revalidated, maybe just to opportunistically try to delete them. Again, I would like it to be reference count, but apparently that's a bit difficult. In any case, we're working on resolving this. The problem itself is well understood. It just seems that the implementation to fix it is slightly non-obvious. So I am happy to say that they are the only problems I know of. and I would have been happier to say that this was my first assignment when I went to Corigine. I got assigned this project. It's been going on for a while, so I'll be very happy not to present on it again next year. So thank you very much for your time.
Thank you so much, Simon. That was a wonderful presentation. Now we're gonna open up for questions. If anybody, I see one back there. I'll go this way.
Simon, I don't think you're going to get out of it then. Good luck on that. So I hear, this might be an out of context question, so forgive me if I am completely off. I hear a lot about BPF. Does that benefit at all from all this, or is this really an OVS hardware offload?
Yeah, so the hardware I'm talking about, well, this solution works on a range of different hardware, some of which can do BPF offload and some of which cannot. I don't think the topics are particularly connected. Sorry.
We have one question back here, sir.
I actually have 2 questions. One thing is about the change of the hardware policy, where you said that you program the meter and then you look at the hardware policy. But I think there is a problem if someone changed the policy right in the middle, saying I'm having both, and then because the meters still stay programmed.
Yeah, I was worried about that too.
Yeah.
We should check what I was hoping is in fact that things get flushed out.
Yeah.
I'm not sure that you can change it like that.
Yeah.
But
Okay.
if you can, there's a problem.
Yeah. I'm just saying because we use for debugging a lot of times if we don't know if it's a hardware problem or not. What we do is we flip to software only.
Right. But
and then back again.
But I understand you can do that, but I think at that point a lot of things get flushed.
Yeah, but I don't think the meters get flushed because they only get programmed once they are configured.
That's a problem.
So I think that's the problem. So
Okay.
that's one thing that you might want to look at. And then the other thing I have about the dummy action, there was some discussion that some hardware offload vendors might not support it because it's a dummy thing that you add.
Yeah.
So I'm wondering if that is sorted out.
The implementation I've seen at the moment doesn't actually require the hardware to do this. It's just a software thing. Because just the way the framework works and then the way it counts things. But certainly, yeah, that is a concern.
But the mic is gone, so I'll speak up a little bit. But is it the hardware that needs to count it, right? So if that action is not present in hardware, will it then still count the hardware part?
The thing is that the hardware is already counting the flow distance, which is what you really want. It's kind of like an indirection mechanism to get this through the API later.
Okay, yeah, as long as it works with all the vendors.
But I have the same questions, to be honest. I have to be honest, I did design this in the first place, but I didn't implement any of the code. It's my team and the people from NVIDIA did all the.
Okay, cool.
All right, thank you so much.
Thank you very much.
Elko, thank you so much, Simon.